Welcome! Have you ever noticed that vibrations are everywhere around you? Think about vibrations in musical instruments, water waves, alternating electrical currents, or the motion of large buildings. Did you know that these vibrations can be described by second-order differential equations? The solutions of such equations are vibrations that can be expressed as linear combinations of sines and cosines. In this video, we will show that such a linear combination can be simplified to a formula containing just a single sinusoid. This result is known as the harmonic addition theorem. Consider the following mass spring system. A little card with mass m is attached to a solid wall with a spring constant k. As the card moves away from its equilibrium position by a distance u, the spring will pull back with a force that is proportional to u. In this way, the card will oscillate back and forth. Let's assume for the moment that the mass of the card is equal to 1 and the spring constant is equal to 4. The motion of the card is then described by the following homogeneous second-order differential equation: u double prime plus 4u equals 0. What are the solutions of this differential equation? First of all, note that the function u of t equals cosine 2t satisfies the differential equation. Also, the function ut equals sine of 2t satisfies the equation. Indeed, any linear combination of these sines and cosines satisfies the differential equation. That is to say, u of t equals a constant times cosine of 2t, plus another constant times sine of 2t. In order to find the constants c1 and c2, we can use initial conditions for the position and the velocity of the card. For example, u at time 0 equals 3 and u prime at time 0 equals 8. You should verify that in this case c1 must be equal to 3 and c2 must be equal to 4. Now we simulate the motion of the card and see what the solution actually looks like. It appears as if the card oscillates like a single sinusoid. There's no sign that this graph is actually the sum of a sine and a cosine. Or is there? Notice that the graph of the solution looks like a cosine which is slightly shifted to the right. And also the amplitude of the oscillation seems to be larger than 3 or 4. Indeed, our solution can also be described by a formula u equals r cosine of 2t minus delta, where delta accounts for the shift of the cosine and r is the amplitude of the oscillation. We will now analyze our formula for ut and try to verify this result. Can we calculate the values of r and delta? Let's first consider the term 3 cosine 2t. A nice and convenient way to visualize this term is to picture a vector in the plane. The red vector in the picture has length 3 and an angle of 2t with respect to the horizontal axis. Notice that the horizontal component of this vector is exactly 3 times cosine of 2t. As we increase time, the horizontal component of this vector starts oscillating about the origin and produces the graph of 3 cosine 2t. In a similar way, we can visualize the term 4 sine 2t. We draw a blue vector in the plane of length 4, perpendicular to the red vector. In this case, we have an angle of exactly 2t radians between the negative vertical axis and this vector. It's not hard to see that the horizontal component of the blue vector is exactly equal to 4 sine 2t. As we run time, the horizontal component of the blue vector indeed produces the graph of a sine. Now that we have visual representations for cosine and sine, we are ready to derive the harmonic addition theorem. That is, we can find numbers r and delta such that 3 cosine 2t plus 4 sine 2t equals r cosine 2t minus delta. Let us add up the two vectors using a head-to-tail construction. The resulting vector, shown in purple, now has a horizontal component that is exactly equal to the left-hand side of the equation, that is 3 cosine 2t plus 4 sine 2t. How about the right-hand side of this equation? Note that the horizontal component of the purple vector must also be equal to the length r of the purple vector times the cosine of the angle alpha between the vector and the horizontal axis. The value r follows from Pythagoras' theorem and is equal to the square root of 3 squared plus 4 squared. The angle alpha is equal to the difference of 2t. This angle between the purple and red vectors must be the delta we were looking for. In this case, it's equal to the arctangent of 4/3. We can now rotate our assembly of vectors. The horizontal component of the purple vector traces out the graph of a cosine that is slightly shifted to the right. Finally, the resulting formula for a linear combination of sines and cosines can be generalized to this formula that works for any linear combination of sines and cosines for any angular frequency omega. Be careful, since the range of the arctangent is limited between -½ pi and +½ pi, an extra pi has to be added when C1 is negative. That's all for now. Now that you know about the harmonic addition theorem, you're ready to study more general second-order differential equations. See you in class.